Hello everyone, welcome to this session of experimental biochemistry. This is the week 3 question answer session, and this is conducted, this NPTEL course named experimental biochemistry is conducted by Professor Shagota Dasgupta and Professor Shomode, and I am Beas Mukherjee, a research scholar from the School of Bioscience, IIT Kharagpur, and today we will be discussing some topics of these of this week 3 lessons. So today we will be talking about electromagnetic radiations, electromagnetic spectrum, and then we will look into the details of spectroscopy. We will learn about absorption spectroscopy, UV visible spectroscopy, and also fluorescence spectroscopy. And then we will solve the related MCQs. So we will begin in some time from now. And I recommend you to attend these classes and watch the video completely, because this is going to brush up your very important concepts. We are going to brush up on the important concepts, and so this is going to help you to actually solve questions in the different competitive examinations. So let us begin with the topic. So let us talk about electromagnetic radiations first. Electromagnetic radiation is defined as the propagation of energy through vacuum or any medium at the speed of light. So I will be using this marker today. It makes it easier. So if you look at this diagram, this is the axis of propagation of the wave. Okay, now interestingly, in this wave, the waves that we see coming from the sun or any other electromagnetic radiation, so this is actually made up of 3 different components. So first one is the electric field, and this is oscillating in a particular direction. The next one is the magnetic field, which is oscillating in a direction perpendicular to the direction of the electric field. And then there is the direction of the propagation of wave. So this is actually perpendicular to the direction of both this electric field and the magnetic field. So according to quantum theory, electromagnetic radiations is a flow of photons. So photons are the packets of energy, or so these are actually moving. This is also called light quanta, and they are moving at the speed of light. So now electromagnetic radiations includes a vast spectrum of energy, ranging from very low energy radiations such as radio waves and microwaves to very high energy radiations such as gamma waves. So some common forms of electromagnetic radiations includes microwaves, television waves, radio waves, infrared radiation, etc. Give me a second. Okay. Okay, so each form has different wavelengths and energy levels, and we will be learning about all of these different types of electromagnetic radiations in details now. Alright, so let us look into the properties of the electromagnetic radiations. So one, you know that all of these electromagnetic radiations, they travel at the speed of light. Okay, that is one important property. Next is, this is a wave. So that means it is going to travel in this way. It travels, this is the direction of the propagation of the wave, but then it actually oscillates around this axis. And so this how high it is oscillating, that is actually the amplitude from this particular axis. And then you take this crest and a trough. So the higher ones are called crest and the lower ones are called trough. So one crest and one trough together makes one wavelength, which is represented by lambda. Alright, so electromagnetic radiations are known as transverse waves, which means that the oscillations of the electric and magnetic field, as I told you, they are perpendicular to the direction of the wave propagation. Okay, so how exactly are these electromagnetic radiations generated? Well, they are formed when charged particles such as electrons, they move. Okay, and when these charged particles are in motion, they are actually accelerated, and these accelerated particles actually result in the formation of oscillating electric field. That results in the formation of these electromagnetic radiations. So these particles carry energy as they travel, creating a wave-like pattern of electric and magnetic fields. Alright, now see wavelength, this is represented by lambda, frequency is usually represented by f, and frequency gives the number of wave cycles per second. So the frequency, the definition of frequency is actually 1 by wavelength. Alright, so this is one full wave cycle, and the number of wave cycles per second, that is basically frequency. So next comes is amplitude. Amplitude is, for example, if you take a pendulum, for example, this is hanging from this point of support, and then what happens, this pendulum, you just push it from here. Okay, you apply a force like this, and then this pendulum moves and it comes here. So this entire position, this from its mean position to this new point, this is called displacement. So this is the displacement of the pendulum, and amplitude refers to the maximum displacement of a wave. So this again of course comes back, right? So this maximum displacement from its equilibrium position, this is termed as amplitude. So all electromagnetic radiations travel in vacuum at the speed of light, which is 2 into 10 to the power 8 meter per second. Okay, or you can also say 3 into 10 to the power 8 meter per second if we round that up. Alright, so now what are the different electromagnetic radiations that are present? So let us look at this. There are a wide range of electromagnetic radiations. So when you look at sunlight, actually majority of these electromagnetic radiations are actually coming towards us. But of course, some of them are blocked because of the stratosphere and the troposphere and mesosphere, all of these layers of the atmosphere, they are actually blocking quite a big part of these electromagnetic radiations. But actually, sunlight in real actually is made up of all of these different radiations. So if you look at this portion, this highlights the different frequencies at which these waves are present. So based upon the frequency and the wavelength of the different types of radiations, they have been grouped and they have been named as well. Okay, so this is gamma radiation. Gamma radiation is having wavelength around 10 to the power minus 15 to 10 to the power minus 10. So this is from 1 angstrom to 10 to the power minus 5 angstroms. So this is the wavelength. Then comes in X-rays. Then it is ultraviolet radiation. And this tiny portion that we see, which is 400 to 800 nanometers, this is actually visible light. And 400 nanometer around lies over here in the range of violet light, and 800 nanometer lies here at the range of red light. Then comes in infrared radiations. So all of these radiations are not visible to the naked eye. So infrared radiation is basically important for heating up the earth. Okay, so all the heat that comes from the sun, that is nothing but these infrared radiations. So then there are radar waves and microwaves, television waves, radio waves. So we will be looking at all of these in details. So here this side even tells you about the different energies of the radiations, and this tells you about the wavelength of the different radiation. Okay. So what makes up the electromagnetic spectrum? The electromagnetic spectrum is a range of frequencies, wavelengths and photon energies with frequencies from below 1 Hz to 10 to the power 25 Hz, corresponding to all the electromagnetic radiations in the increasing order of frequency and decreasing order of wavelength. So if you look at this, this is actually decreasing order. So if you look from here, this is decreasing order of frequency, and this is this is actually increasing order of wavelength, right? So this entire thing together makes up the EM spectrum. Okay, so this table gives you a better idea of the wavelength and the frequency and the energy of the different radiations, which are the components of the electromagnetic spectra. So you can go through this and try to remember, if nothing then at least these last digits, because questions will be there where you will be asked about the wavelength of, say, X-ray or wavelength of UV light. So all these questions might be asked, alright. So you can actually go through this table. Next, let us look at the applications of the electromagnetic radiations. Now all of these radiations are coming to the earth. Okay, understandable. But then how is it helping us? So firstly, this radio waves. Okay, so radio wave is having a wavelength of more than 1 millimeter. So this is quite high wavelength. If the wavelength is high, that means the frequency is less. Okay, so this is, radio waves are used in communication and in broadcasting. Okay, then comes in the microwaves. Microwaves range from 1 millimeter to 1 meter. Okay, so this is around cooking. So this is used for cooking, then radar and satellite communication. Infrared radiations range from 700 nanometer to 1 millimeter, and these are thermal, these are involved in thermal imaging, remote controls, etc. So visible light ranges from 400 nanometer to 700 nanometer, and this is of course used for human vision, and this is used for optical communication. So visible light is the thing that gives color to everything we see. So the world is so colorful and so beautiful to us because of the visible light. So what happens, matter actually absorbs light and then it gives out. Okay, so it absorbs and then it gives out light. So the light that it reflects, that is the one that we see, and what it scatters and gives out, so that is the one we see. So then comes in ultraviolet light. So ultraviolet radiations range from 10 to 400 nanometer. So this is used in sterilization, and because ultraviolet light is fatal for organisms, and so therefore it is used for sterilization, which is cleaning of utensils and then cleaning of surgical instruments, lab instruments, because this actually kills the microorganisms. So UV lamps and forensics. Okay, X-ray. X-ray, we of course know that this is used, this does not pass through human bones, and so this is used for imaging. So see, medical imaging and security screening. Then comes in gamma radiation. So gamma radiation is having very low wavelength. So that means it is going to have very high frequency and it is going to have very high energy. So this has so high energy that it can completely penetrate matter and it can pass through. So gamma radiations are produced by nuclear decay. So this is used in medical imaging, cancer treatment. So cancer treatment, what happens, the tumors, these are actually treated by using these non-surgical methods where gamma radiations are utilized. And then nuclear medicine. So if you look at this diagram, this tells you about the application of X radiation. Right, this is what white light I was telling about. So white light comes in, and this is a glass prism which disperses white light, and you can see all of these different colors. So this is VIBGYOR. If you take from violet to R, this only the initials of the names of the alphabets, so that makes VIBGYOR, and this is what we see around us. All right, and this is the heat waves that are coming from the sun. So this is actually caused by infrared radiations. Okay, so let us look into the applications of EM radiations in a little more details, because all of these competitive exams, they are they sometimes ask the applications of EM radiations in the form of match the following questions. Okay. So we will have a look at these. So look at gamma radiations. Gamma radiations are biohazardous in nature. Yes, because they can pass through matter. They can completely penetrate your skin and they cause various types of anomalies in the skin. So they can be controlled and used in various important purposes. So one of them is used in the treatment of cancer without surgery. So the cancerous tumor is subjected to gamma radiation which kills its DNA. Okay, it causes some kind of mutations in DNA and then it actually kills the cell. Next, what comes in is sterilization of surgical instruments. So this is also used in the food industry to kill harmful bacteria. Infrared radiation is also referred to as heat or thermal waves as they have a heat inducing property. So infrared radiations are used to make infrared heaters and they are also used for therapeutic purposes involving heat. Okay, so now infrared radiations are further classified into near infrared and far infrared. So near infrared are used in the electronic applications such as TV. Yes, so they are used in the electronic applications such as TV and 1 minute eraser. Okay, so they are used in the infrared radiations. Yes, so near infrared radiations are used in the electronic applications such as TV remote sensors and photography. So far infrared rays are more thermal and anything generating heat gives out these far infrared radiations. Even human body at 37 degrees centigrade gives off infrared radiations of around 800 nanometer wavelength. Alright, so you can refer to this table if you want. This tells you about the near infrared radiations and the wavelength of the near infrared radiations, and they also tell you the applications. Okay, you can go through this if you are interested. So see here, far infrared radiations and the wavelengths are around 15 to 1000 micrometers. So that is used in cancer therapy. So I am not sure if such details will be asked in the examinations, but you can just go through if you are interested. Okay, so we move on to the week 0 assignment. Now here only selective questions have been chosen that are very relevant in this in today's topics. Okay, so we will try to solve them and then we will try to brush upon some other topics and then we will solve the questions related to those topics. Anybody wants to? Yes,
madam. Assignment third.
Yeah. We'll come to assignment third. See, this is assignment week 0 and then there's only one question. So after that, we'll go to assignment third. Alright.
Thank you, madam.
Okay.
Thank you, madam.
So let us carry on with this. So the first question is, UV light has a wavelength range of 0.1 nanometers to 10 nanometers. Then 10 nanometers to 400 nanometers, 400 to 700 nanometers and 700 nanometers to 1000 nanometers. Now firstly, when you see this question on paper, you will feel like this is something that I will have to remember, I'll have to mug up, I better skip this. But do not skip this because this is a very direct question. Because if you remember the wavelength of visible light, I am sure everyone remembers the wavelength of visible light, which is 300 nanometer to 700 nanometer, right? Or 400 nanometer to 700 nanometer. That is the wavelength of visible light. Now UV has wavelength what? Larger. It has wavelength longer than visible light. So that means it should be this. Sorry, UV has wavelength shorter than visible light, right? So let us look at the answer. Yes, so if you look at this answer, UV has wavelength which is 10 nanometers to 1000 nanometers. and this is the wave, so 10 nanometers to this 4000 nanometers. So 10 to 400 nanometers, because this is 400 and this is 7000 nanometer. And so what you need to do is you just have to find the periphery of the wavelength of the visible light, and then you can solve the question. So this is actually the wavelength of the visible light, and then you just have to find the periphery of it, which is 400 to 10, and then you can get the answer. So B is the answer, which is 10 nanometer to 400 nanometer. Okay, so now coming to week 3 assignment. Alright, so this question is also very related. Look at this and tell me what do you think is the answer. So the question says, which region in the electromagnetic spectra has the wavelength of 0.01 to 10 nanometer? Now we know that 10 nanometer is definitely UV. So 10 to 400 nanometer is UV. So who was there before UV in the EM spectra? Try to answer this question. Okay, so firstly, this definitely gets cancelled. Infrared region cannot be that, because if this is the visible light region and we know that this is UV light, then infrared is supposed to be here, right? So they have asked which region of the spectra has wavelength this. So it cannot be infrared. So this gets cancelled. Now they are asking who is going to be here. So who is actually here? Who is before UV? Okay, so let us find out the answer. So before UV it is X-rays, right? So then the answer should be A, X-rays. Now this is another graph, another table that gives you the different types of radiations, the frequency of the radiations in hertz, and the wavelength of the different radiations. You can use this again and again to remember, to at least brush upon this topic. Okay, now so we have understood that these are the different waves that make up the electromagnetic spectra. Now how to find out what is the energy of the electromagnetic spectra, what is the frequency of the different electromagnetic radiations, because we already know that the speed is the same, right? Speed is after all the speed of light in case of all electromagnetic radiations. Now what about the energy and the wavelength and the other parameters? So this is the formula. I'm sure everybody remembers this from school. So E is equal to hc by lambda. E is the energy of the radiation. This is valid for any wave. So E is the energy of the wave. H is Planck's constant, and the value of Planck's constant is given here. And then C is the speed of light. Speed of light is also given here. And then lambda is the wavelength of light, right? So that tells you that energy of a particular electromagnetic radiation is directly proportional to the frequency, because if you look at this equation now this H and C, what happens is F is equal to C by lambda. This also we know, this is frequency. So frequency is equal to speed of light divided by the wavelength of light, right? So then E is equal, okay, so that tells us that, see, lambda is inversely proportional to energy, that means, and also lambda is inversely proportional to frequency. So that means energy would be directly proportional to frequency, that we can see in this equation. So F is equal to E by H, right? This is how all of these terms are interrelated. Now we will solve a question based on this knowledge. Alright, try this question out. So the question says, if the frequency of radiation is increased by 2 times, then what would be the change in the energy of radiation? Okay, so we know the equation. This is my E is equal to hc by lambda, right? And we also know F is equal to what? E by H. Right? This is something that we already know. So they are saying that if the frequency is increased by 2 times, so if this is becoming 2F, then what is going to happen? So if this is becoming 2F, H is a constant, right? So energy is obviously going to become 2E to balance the two sides. Then what would be the change in radiation? What would be the change in the energy of the radiation? So energy should become 2 times. Let's look at the answer. So it is proportionally increasing with its frequency. Yes. So it is correct. Energy is also becoming 2 times. So this is a very simple question, right? Then comes in the concept of spectroscopy. So we have understood until now that all of these various electromagnetic radiations are coming to the earth. Okay. Now what happens when these electromagnetic radiations interact with everything that is there on earth? That is matter. Okay. So what matter has a very interesting characteristic. Matter actually absorbs these electromagnetic radiations and then it emits light of different characteristics, okay, of a different wavelength. So it can react with light in various ways. Firstly, there is reflection, right? So it can just reflect all the light that came to it. It can also, for example, glass is reflecting the light, right? And again, it also depends upon the wavelength of the light that is coming. For example, you looked that gamma radiations are so powerful, so strong that they can pass through matter. Okay. And then what happens? It can absorb light, it can scatter light. So all of these different things are happening when light or electromagnetic radiation is actually interacting with matter. So this is the basis of spectroscopy. Spectroscopy is nothing but the study of how these electromagnetic radiations are interacting with matter and what it is causing. So see, spectroscopy is a technique used to study the interaction between matter and electromagnetic radiation. So this involves analyzing the spectra of emitted, absorbed or scattered light to gain information about the composition, structure and properties of the materials. Okay. So now this table lists out different spectroscopic techniques. So there are so many different spectroscopic techniques and they use wavelength of different range and then they have various applications. So we will go through them briskly and then we will learn about the ones that we are more interested in this course. Okay. So the spectroscopic technique first comes in atomic absorption spectroscopy. So this is a type of absorption spectroscopy. So this is a very important tool to actually find out about the structures. Okay. So wavelength range, visible and ultraviolet. So the application is elemental analysis and environmental monitoring. Next comes in infrared spectroscopy. So infrared spectroscopy, the wavelength range is given here and this is used for identifying the functional groups in organic compounds and analyzing polymers. Okay. So next is UV visible spectroscopy. So today we will be looking into greater details in this one. UV visible spectroscopy. So UV has a wavelength range of 200 to 400 nanometer. You can also say 100 to 400. And then visible light has a wavelength of around 400 nanometer to 700 nanometer. So all of this is detected in the UV visible spectroscopy and this is used for quantitative analysis. That means this helps to understand the concentration of the sample. It helps to understand the structures of the samples, molecular structures, and it helps to understand the electronic transitions in the molecules. Okay. Then comes in nuclear magnetic resonance. So this uses radio frequency in megahertz. Okay. So that is very, very high wavelength. This is used for solving molecular structures and identifying the compounds. Okay, then it is X-ray absorption spectroscopy. So they of course use X-ray and this is used for studying electronic and structural information in solid, liquid and gases. Then comes in Raman spectroscopy. So this uses again visible and near infrared region and this is used for investigating molecular vibrations. So remember this can come as a question. Okay. So Raman spectroscopy, it is visible light and infrared region. It is used for understanding molecular vibration, material analysis and biological imaging. Alright. So we will be looking at absorption spectroscopy first. So what is absorption? Absorption is taking in of a material, right? So what happens when these electromagnetic radiations come and strike matter? Matter actually absorbs these radiations, and then what happens when matter actually absorbs these radiations? So you know that matter is after all made up of atoms and molecules. So inside the atoms there is the nucleus, and for example, consider this to be the nucleus, and then there are the electrons which are revolving around in their own orbitals, right? So there are electrons in the ground state, which is say represented as N, or I will call this as GS just for simplicity. So this is the ground state. Okay, so let's see that this was an electron with a particular spin half, and what happens when energy, it absorbed energy, the electron gained energy, and then what happens? It transitions from this ground state into the higher energy state. So this is called absorption spectroscopy, the study of this electronic transition on absorption of energy of a specific wavelength. This is h nu. Nu is after all frequency. Okay, so what happens? This particular electron, this would not go up to the excitation state unless a specific wavelength of light comes and hits it. This is called absorption spectroscopy. So the basic principle of absorption spectroscopy, including UV visible spectroscopy, involves passing light through a sample and measuring the amount of light absorbed at different wavelengths. Okay, so different wavelengths at light at different wavelengths will be used to excite this electron, and the extent of absorption is related to the concentration of the absorbing species and the characteristics of the molecular electronic structures. So this works on the principle of Beer-Lambert's law. We will be looking into greater details of Beer-Lambert's law very soon. And absorption spectroscopy is also is used to study. So this technique is studied using absorption spectrophotometer. So this is the instrument which is used to study this technique. Alright, so I will erase this. Yes. So look at the applications of absorption spectroscopy. These are quantitative analysis. This helps to determine the concentration of a solute in a solution, and qualitative analysis. It tells us whether what kind of functional groups and electronic transitions are happening in a molecule, and also monitoring reactions, that is studying the reaction kinetics by tracking changes in absorbance over time. So it even helps to study the dynamics of a particular solution. Okay, so you can do it in different ways. For example, in maybe denaturation studies and all, or maybe unfolding of a protein. So what happens when the protein is unfolded? It is showing some kind of absorbance, and when it is folded, it is going to show different kind of absorbance. Okay, so we will learn all of these in details in the next few weeks of this course. So there is a small thing that I would like to share with you. So consider this as a protein in its folded state. So there is a tryptophan residue. Okay, so now this tryptophan residue, it is actually having this indole ring in it, which is having this kind of conjugate double bond structure, right? So these conjugate double bonds, this is actually something that can absorb light. Okay, so all of these DNA bases, and then the molecules in the residues in the proteins which are having these conjugate double bond structures, they are going to absorb light, and then we can distinguish them into fluorophores and chromophores. So chromophore is something that gives color to a protein, and fluorophore is something that gives fluorescent signals. It emits fluorescent signals on absorbing light. Okay, so consider this tryptophan is there, and it is showing some kind of absorbance. Let's say it is absorbance A. Then what happens? You add some urea into the solution, and this protein actually unfolds. So what happens, the protein is unfolding, it is completely denatured, and this this tryptophan, it was initially buried and now it is exposed to the surface. So what happens, it will now emit light at a different wavelength, and it will have a different absorbance. So this is actually a part of fluorescence spectroscopy, which we will be studying soon. And so here, let's say the absorbance is going to be A naught. So this is how we can distinguish between the structures of different molecules when we are subjecting them to different environmental conditions based on the different kind of wavelength it either absorbs or it emits. Okay. So now let's understand Beer-Lambert's law. Now this is one of the basic concepts of biochemistry, and this comes in every question paper always. So the questions are either simple or they are a little complicated. We are going to solve these questions to get more practice. Okay. So Beer-Lambert's law. Now what is Beer's law? Beer's law states that the concentration and absorbance. So this is concentration written as C, and absorbance we know it is written as A. These two are directly proportional to each other. Lambert said that absorbance and path length is considered this as a cuvette. Cuvette is nothing but this horizontal, it's like a rectangle, but then it's a rectangular box. Okay, so this is a cuvette. So in this cuvette there is this solution, a solute. Okay, let's say a protein, and there is a solution in which this is present, and then you apply some light to it. So this light, actually some of the light is scattered by the protein. So look at this, there is scattering loss. Some of the light gets reflected, so reflection and interference loss. So this does not even reach it, it actually gets reflected to the in the opposite direction, and then some light is absorbed by it and then emitted by it. So this light that gets emitted by it, this is called the emergent beam. So the incident light, it is having an intensity of I naught, and the emergent beam is having an intensity of IT. So this is lower intensity, of course, because some of it has been absorbed by it, right? So this length of the path, what is the distance from one end of the cuvette to the other end that the light traverses when it passes through a solution in a cuvette. This is called the path length of the cuvette. This is usually 1 centimeter, and this is taken as L. Alright, so this is what Beer said, this is what Lambert said. Then people combined the two laws and it became Beer-Lambert's law, and that states that for a given material sample, path length and concentration of the sample are directly proportional to absorbance. Now they have stated that this and this is directly proportional to absorbance. Now you understand that there is a proportionality here, but then to make sure that a proportionality can be removed and an equal sign can be added, there needs to be some kind of a constant that needs to get multiplied. So here, this is the molar absorptivity. This is called the molar extinction coefficient. We commonly refer to this as the molar extinction coefficient. So you can be asked what is the unit of the molar extinction coefficient. So in that case, you will have to say that absorbance is not having any unit. This is having unit centimeter, and concentration is going to have molar as unit, right? So then molar absorption coefficient is going to have an unit molar inverse centimeter inverse. Okay, so this molar absorptivity, extinction coefficient is a property of the solution. Yes, it is a property of this particular analyte that we are measuring, and this depends on the fluorophores or the chromophores that are present in this analyte. Okay, so if you look at these equations, absorbance is equal to log 10 of I naught by I. So I naught is this incident beam, and T or I is the intensity of the emergent beam. Alright, and also log I naught by I is equal to epsilon into L into C. So basically you are equating this intensity of the light with the absorbance and the concentration of the solution. Alright, so now we will look at UV visible spectroscopy. So, UV visible spectroscopy is a kind of absorption spectroscopy. Now, by the name, you can very well understand that UV visible spectroscopy is the study of interaction with UV light and visible light with matter, right? So, UV light means that is from wavelength 150 to 400 nanometer, and visible light means it is from wavelength 400 to 800 nanometer. So then what is the light source? See, look at this figure. You are using tungsten lamp for normal visible light. They are using a normal tungsten lamp, alright, for this visible light. And then they are using deuterium lamp for UV radiation. So that is represented as D2. Okay, because deuterium is D2, right? So then it provides a beam of light that passes through the sample. Okay, so monochromator is like a window. So this window, it is allowing only a specific, so for example, this is a window, okay, it is having a small slit and a lot of people are coming in, and but only the ones who are having passes will be allowed inside. Okay, so these are all blocked, but then only the one that has the pass is allowed to go. So this is actually monochromator, and all of these people, let's say this is a door. Okay, so all of these people that are coming in, these are actually different wavelengths found in white light or electromagnetic radiations, and only the one that passes has a specific lambda. So this is a monochromator. It is allowing only light of a single color. So mono is single and chromator is particular wavelength. So light of a particular wavelength to pass through. So see here, this is actually, so light is coming, it is getting reflected, it is coming here, and this is the entrance slit. So all the light comes in, but then there is dispersion and it is allowing only one specific, this particular blue light is only allowed to pass through. And then what happens? Blue light is allowed to pass through the sample. So here they have showed this in the form of two different beams of light are going. One is going through the reference and one is going through the beam splitter. Now this is a double beam spectrophotometer. You can also have a single beam spectrophotometer where the single cuvette is actually used for both recording of the reference and the sample. Okay, so sample holder contains sample in the solution. Quartz cuvette ensures minimum absorption of UV light by glass and maximum by the sample. So what happens when we are using this UV radiation? We usually use quartz cuvette. Why? Because glass actually absorbs quite a lot of UV light, but then quartz, it is a material which does not absorb much of UV light, and therefore all of this absorption, most of the absorption is going to come from the sample and not from the cuvette, material of the cuvette, and therefore the estimation of the concentration of the solutions will be correct. Okay, and then there is detector. So this is going and then it is detected and then data processing is done, and see here you're getting the output. Absorbance is there, wavelength is there, and this is how we understand UV visible spectroscopy and how it functions. Alright, so let us quickly solve a question on UV visible spectroscopy. Look at this. Tell me your 1 minute. Okay, so we will look into this question. So the correct path of light in a spectrophotometer is, first is source lamp. Of course, first has to be source lamp, that is true. And then there is the sample chamber. I don't think this is right. Okay. And then there is, the second one says recorder. How can recorder come first? So this two cannot be right. Alright. Then the third one says source lamp. Then there is monochromator. Then there is fluorescence monochromator. And then there is detector, sample chamber and recorder. No. Detector and sample chamber, this is reversed, right? Then there is source lamp, monochromator, sample chamber, fluorescence monochromator, detector and recorder. So then which one do you think is the right answer? Let us look at the answer. So D is, yes?
I said D.
D you said, very good. So D is the right answer, because if you look at this slide, okay, so there is a monochromator, but then they are asking about your fluorescence spectrophotometer. So, and therefore there is fluorescence monochromator. So fluorescence monochromator will be there because we are actually recording fluorescence, the lambda emission here, and therefore this is there. So when I teach you fluorescence spectrophotometry, spectroscopy, this will be clearer to you. Okay, all right. So now we were talking about the fact that different molecules, or the sample molecules, they are going to behave differently in different environment. All right, so for example, this is absorbance. All right, so let us say that we got a peak like this. This is the absorbance and this is wavelength, and we got a peak like this. Then what happens, there is a shift in the peak. So the size of the peak can increase, that is called hyperchromic. The size of the peak can decrease. Okay. So the size of the peak can increase, the size of the peak can decrease, that is called hypochromic. And then this peak can shift towards the red, that is called bathochromic or red shift. And it can also shift towards the left, that is called hypsochromic or the blue shift. So when can all of this happen? So hyperchromic shifts, that is, this can increase, right? So this peak can become higher. That happens when a molecule undergoes a change in conformation, interacts with other molecules, or experiences a change in its environment that leads to increase in the absorbance or fluorescence intensity. So these are the cases when you can observe a hyperchromic shift. Then there is hypochromic shift. What happens in case of a hypochromic shift? It is observed when the conditions lead to a reduction in the absorbance or fluorescence intensity. This can result from changes in the molecule's environment, such as decrease in the solvent polarity or alterations in the molecular structure. Then there can be this blue shift or the hypsochromic shift. This is associated with changes that result in higher energy transitions. For example, a shift in the absorption or emission towards shorter wavelength might occur due to an increase in the electron density or change in the electronic structure of a whole molecule. So basically the change in the electronic structure of the molecule is happening, and therefore the transition from the lower energy level to higher energy level is more. That is hypsochromic shift or blue shift. And then there is bathochromic shift, which is decrease in the energy level. So the shift can occur due to factors such as increase in solvent polarity, changes in molecular structure, and interaction with other molecules. So try to solve this question. So I actually go through the topics and then tell you to solve questions so that you can have a better idea of what the question is asking. Otherwise it becomes really difficult when you look at a question and then you really don't understand what they're asking. It actually helps to improve your confidence when you go through the topics first and then do the like the questions related to those soon after. So see, this is initially how the peak was. Okay, so this is absorbance and this is wavelength. Initially this was the peak. Now the peak has increased in size, that is number one, and it has also shifted. If you look at this line is a little towards the left, right? So that is shift towards the left. So which one do you think is the case? So these are the different kinds of shifts, and they have asked whether it is 2 only, that is whether it is only bathochromic. It cannot be 2 only or 3 only, because see, there are 2 different cases already. So first option is definitely eliminated. So then all the 3 remain. So see, one, there is increase, so it should be hyperchromic, right? That is for sure. So see, only one has hyperchromic, so 3 should be correct. So it is either B or C. Both of these options have 3 in them. And then there is hypsochromic, and then there is bathochromic, right? So which one do you think would be the thing? It would be hypsochromic, because we are shifting to the left, right? So look at this slide. Hypsochromic was blue shift or towards the left, that is higher energy level electronic transition was happening in this case. So this is the case and this is the answer. Okay, and then comes in absorption and emission spectroscopy. So what is the difference between absorption and emission spectroscopy? So in case of absorption spectroscopy, we are more concerned with the wavelength which our molecule of interest is absorbing. Alright, but in emission spectroscopy, what happens? The molecule absorbs a particular wavelength, and then there is electronic transitions in the molecule. So we are going to look into electronic transitions in greater detail very soon. Okay, so the molecule is going to undergo electronic transition, and then the electron gaining energy, it goes from lower orbital to higher orbital, and then it actually comes back. Okay, it goes to the higher orbital and then it comes back to the lower orbital, and here what happens? The energy of the molecule decreases because some of the molecule is lost in between the different vibrational and different states, right? So what happens? Some of the energy is lost, and so if energy is reduced, then the wavelength will be high. So light of a higher wavelength will be released by the molecule when it comes back to its initial ground state, the electron. Okay, so let us look at this differences. So emission spectra, and so when this light that is released, this is the emitted light, this is collected, this forms the emission spectra, and absorption spectra is the light that is absorbed, and that light, if the spectrum of that light is viewed, then that is the absorption spectra. Okay, so emission spectra tells you produce when atoms release energy. Absorption spectra produce when atoms absorb energy. Emission spectra comprise colored lines in the spectra, right? And then absorption spectra comprise dark lines or gaps in the spectra. Okay, it is helpful in figuring out the composition of certain matter. Can be used to figure out the ability of certain objects to retain heat and its absorption level. So the types of photons emitted is helpful in figuring out the kind of elements and the substance is made of, as each element radiates a different amount of energy and has a unique emission level. Okay, so the emission spectra of a particular molecule can tell you about different properties of the molecule. Similarly, the wavelengths of light absorbed is helpful in figuring out the number of substances in the sample. So again, this can also tell you about the different characteristics of the sample, right? So both of these actually tell you about the characteristics of the sample. So fluorescence spectroscopy actually works on the principle of emission spectroscopy. So we will look at this Jablonski diagram. So whatever I was telling you until now, all of that plus more has been depicted in this diagram. So Jablonski diagram is a graphical representation used in the field of spectroscopy to illustrate the electronic transitions that occur in a molecule when it absorbs or emits photons of light. Okay, so initially this is the ground state of an electron. So electron was here peacefully. Then what happens? Some radiation of specific wavelength come and strikes the electron. Now the electron gains energy and then it goes to higher energy orbital. Okay, so that is called absorption, and this all that is shown in green is your absorption, right? Now what happens? These are the, now see, this is one particular let's say energy level, and then this is one particular energy level, but then every major energy level is actually divided into minor vibrational and other thermal and vibrational energy states. So these are different vibrational energy states, and they are having very small minute energy differences between them. So what happens after absorption, this electron comes from this higher energy level to another higher energy level, and as it comes there is a non-radiative decay. Okay, so some of its energy is lost. This is called internal conversion. Okay, and then what happens is there is inter-system crossing. So we will look at these terms because these are very very important and they will be asked in your exams. So what happens, these vibrational energy states, the molecule is the electron is crossing, and what happens when the electron comes straight back and it emits a particular wavelength, light at a particular wavelength, that is the lambda emission, and that gives the fluorescence. All right, then what happens, there is inter-system crossing and the electrons go into a triplet state. So all of this is singlet state. I will tell you about that very soon. So this is, the electrons are in singlet state, but then when there is inter-system crossing, this T1 represents triplet state, and so from the triplet state it comes back to its original non excited state, the ground state, that is called the phosphorescence. Okay, so let us try to understand what is the difference between fluorescence and phosphorescence, plus what is the difference between singlet and triplet state, and also the differences between internal conversion and intersystem crossing. Okay, so Jablonski diagram provides a visual representation of the energy levels and transitions between electronic states within a molecule. Alright, so what are the different key features of a Jablonski diagram? Now let us go back to the diagram and try to find out. So the first one they say is electronic state. Of course, this is the lower energy state, this is the higher energy state, right? So it depicts different electronic states of a molecule such as the ground state or the lowest energy and various excited states of the higher energy. Then there are transitions. So all of these direct arrows, right? These direct arrows are the movements of the electrons. So this is transition of electrons. And then let us find out what these arrows, dotted arrows, mean. So see, transitions, arrows on the diagram represent possible transitions between the electronic states. These transitions are associated with absorption or emission of photons. Okay, so when absorption of photons happens, the electrons are energetically more favorable to go into the higher energy states, and then they come back to the ground state again by emitting photons in the form of energy. Then what happens? Energy levels. The vertical axis represents the energy levels of the electronic states, with higher energy levels positioned higher on the diagram. So this is the energy axis, right? So higher you go, more is the energy of the orbital. So these are the higher energy states, and these are the energy states that are having medium energy, and then these are the lower energy states. Then what happens? Non-radiative transmission. So all of these dotted lines, these are actually non-radiative. So some transitions are non-radiative, meaning that the energy is transferred within the molecule without the emission of light. These transitions are often represented by wavy lines. So look at these wavy lines. These are actually non-radiative decay of energy. Then there is radiative transition. Other transitions are radiative, involving the emission or absorption of photons. They are represented by straight arrows. Alright, so this is going to give you the difference between fluorescence and phosphorescence. Now, this is also important for examinations. Let us have a look. So, in the context of Jablonski diagram, an internal conversion and intersystem crossing are two types of non-radiative transitions. 1 minute. Yes, so to understand fluorescence and phosphorescence, we need to understand internal conversion and intersystem crossing. So, and then we will be going through a little more of fluorescence spectroscopy, and we will be done with the theory, and we will only solve questions. But then to be able to solve the questions fluently, we will have to be looking at these a little. Okay. So fluorescence and phosphorescence. So in the context of Jablonski diagram, internal conversion and intersystem crossing are two different types of non-radiative transitions that describe the ways in which a molecule can return from an excited state to a lower energy state without emitting a photon. So internal conversion, look at this. This is a type of non-radiative decay in which the energy of an electronically excited state is transferred to a lower electronic state within the same molecule. So the internal conversion is typically represented by wavy lines connecting different electronic states. And this process involves the redistribution of electronic energy among various vibrational and rotational modes of the molecule, ultimately leading to transition to a lower electronic energy state without the emission of light. So look here, this is internal conversion. What happens from a higher to lower energy state they are coming, and then these are the rotational and vibrational energy states. So there is redistribution of energy in the same molecule without emission of energy in the form of light. Next comes in intersystem crossing. So what is intersystem crossing? We'll go through it quickly. This is another non-radiative process, involves transition between different spin states. So singlet and triplet. In the Jablonski diagram, intersystem crossing is represented again by wavy lines and usually connecting with different spin multiplicity. So we will look at this very soon. This process occurs when the molecule changes its electronic spin without emitting a photon. For example, singlet state may transition to a triplet state. So now we are stuck with two different questions. The first one is, what do you mean by singlet and triplet state? And the second one is, what exactly is fluorescence and phosphorescence? Okay. So singlet and triplet states are used to describe the different spin configurations of an electron. So look at this. Initially the electron was having this plus half and minus half spin. Then what happens? It was in the lower energy orbital, and then it went to the higher energy orbital, where it is now having a spin that is opposite to the spin that was initially having. So this is the case in fluorescence. Okay. But then what happens in case of phosphorescence? In phosphorescence, see here, there is no change in spin. So this electron, it remained here, and this electron, it went here. So there is no change in spin. So it is going from pi orbital to pi antibonding orbital. Okay, and here it is going from pi to pi antibonding orbital, and then again there is initially there was no change in spin, but then there is change in spin. So here there was no change in spin initially, and then there is change in spin. So see, this is no more facing upward, rather it is facing downward. This guy, it was here and it is still here, right? So there is actually a change in spin. So this is what a triplet state is, where there is change in spin. So this spin multiplicity is related to the number of possible orientations of the electron spin. So in this case it is 0, because 2s plus 1 is 1, and here this is 2s plus 1 is equal to 3, where s is 1. So here the spin is actually 1, right? Because both of these are pointing in the same. So that is not plus half and minus half. It is either both minus half or both plus half. That is why it is 1. That is what spin multiplicity is. Okay, this is just a probability of the number of possible orientations of the electronic spin. So spin configuration, see, all the electrons are paired, and all the electrons, two electrons have parallel spin. One is having opposite spin. So this is more common. Singlet state is more common in case of fluorescence, and triplet state is more common in case of phosphorescence. In the singlet state, all electron spins are paired, resulting in total spin 0. In the triplet state, two electrons have parallel spin, resulting in a total spin of 1. Right? So singlet state is seen in fluorescence, whereas triplet state is common in phosphorescence. Now this is fluorescence spectroscopy. So in case of fluorescence spectroscopy, what happens is, this is the xenon lamp which is giving light. This is getting reflected by the mirror. It is coming to the monochromator. Monochromator is selecting the specific wavelength. Now if you look at the question that we solved just 5-10 minutes back, they were asking you about the path of light, and they were asking you about this emission monochromator and excitation monochromator. So excitation is synonymous with absorption. All right. So here one specific wavelength is getting selected, which is going to the sample, and then it is going from the sample to the emission monochromator, which is selecting again one specific wavelength amongst all of these that are emitted by this sample, and then this is going to the detector, then data processing is happening, and then it is giving you the output, right? So fluorescence occurs when a molecule absorbs light at a specific wavelength, which is called its excitation wavelength, and it undergoes a brief transition. So it undergoes a brief transition to a higher energy state and then returns to the ground state by emitting light at a longer wavelength. So this light that is emitted, this is actually at a longer wavelength, meaning it is having lower energy. The emitted light is called fluorescence. So this emitted light is nothing but fluorescence, and its intensity and wavelength can be measured to gather information about the sample. So fluorophores are the molecules that are capable of absorbing and emitting light of longer wavelength. So coming to tyrosine, tryptophan and phenylalanine, I was telling you just recently how these are intrinsic fluorophores and they are capable of absorbing and emitting light because of their conjugate double bonds in their structures. Okay, and GFP, which is green fluorescent protein, and ETBR are extrinsic fluorophores. GFP is a protein and ETBR is a molecule which is added to visualize DNA. So this much is clear, I'm sure. And then also there are other concepts. So we will take a break of 5 minutes and then we will quickly finish this. Discard. Yeah, so we are nearly done. So just 2 more slides are left, and then after that we will go into the questions. So let us take a break for 5 minutes and then we will be back soon. Aye. 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 এই বাবা আমার নেটওয়ার্ক বেরিয়ে গেল, দেখেছি আমার ফোনে ডেটা শেষ হয়ে গেছে। আমি ওটা রিচার্জ করছি। না, তোর মাসিমার ফোনটা নিয়ে আসবি, একবার গিয়ে আমাকে দিয়ে দিতে। হ্যাঁ ওরটাই দে তাহলে, তো দিদিরটাই দে। দিদি আমার ফোনটা চাইছি, ফোনটা চাইছি আপনার, মনে হচ্ছে না। এই আমার শেষ হয়ে গেছে ডেটটা, আমাকে ফোন। হ্যাঁ হ্যাঁ জলদি দিতে বলো। হ্যাঁ I'm so sorry I got disconnected. Okay, so we will resume in 2 minutes. Okay, so we were looking at fluorescence spectroscopy. right? So in the previous slide, we understood the instrumentation of fluorescent spectroscopy, and we also had a look at the fluorophores. We had a look at what fluorophores are. All right. Now there is another important concept. So the difference in wavelength between excitation and the emission peaks should be more than or equal to 10
Your
nanometers.
sound is not able to listen, madam.
Sound, you're not able to listen. Okay, thank you so much for pointing out. Okay, is it clear now?
Yes.
Okay, so let us resume. So in the just in the previous slide, we learned about fluorescence spectroscopy. We looked at the instrumentation. We looked at the concept of fluorescent spectroscopy and what fluorophores are. All right. Then comes in a very important point, which is Stokes shift. So Stokes shift is valid in case of spectroscopy. So what happens? For example, this absorption spectra of a molecule, I'll take the pointer, that will be easier for you to understand. So for example, let's say that there is a donor fluorophore. Yes. So there is a donor fluorophore. It absorbs wavelength at a particular wavelength. It absorbs light at a particular wavelength, and then there is a emitter fluorophore. Okay. So this emits light at a specific wavelength. Now this is the maxima, this peak for this donor fluorophore. Let's say this is absorbance, and this is the axis for wavelength. Okay, and this is the donor fluorophore. 1 minute. Discard. Yes. Anybody wants to join? No. All right. So we'll resume this. Okay. So yeah. Now in a single molecule, there is pen, right? So let's say this is the graph, and there is a donor molecule and there is a recipient molecule. Both of these are fluorophores. Okay, so the donor molecule absorbs at this particular wavelength, and hello, anything you want to say? So the recipient molecule, it emits light at this particular wavelength. Now this is called the lambda absorption, and this is also called lambda excitation, and this is called the lambda emission. All right. So the difference between these two wavelengths, this should be minimum 10 nanometer. This is called Stokes shift, so that the wavelength that is actually exciting the donor is different from the wavelength that is, so that means the donor is absorbing at a particular wavelength, it is giving out light at a particular wavelength. This wavelength the recipient is absorbing, and then the recipient is giving out a light, and this light we are detecting. So this is a major component of fluorescence resonance energy transfer. Okay, so this energy and this energy should be significantly different, and that is what Stokes shift says. Okay, so the applications of fluorescence spectroscopy. So fluorescence spectrophotometer is the device, you saw it, and it is different from the absorption spectrophotometer in this particular aspect. Firstly, the sample and the monochromator or the detector is present at right angles to one another. That is point number 1. And the second point is this particular emission monochromator, which is an additional thing in the fluorescence spectroscopy spectrophotometer. Alright, so what are the different applications? So, fluorescence spectrophotometers typically consist of light source, usually a high energy lamp or laser, a monochromator, and emission wavelength. Monochromator to specify the excitation and emission wavelength, and a sample holder and detector to measure the emitted fluorescence. So, this is used for biomolecular studies, where you can study the structure, dynamics, and concentration of different biomolecules. Then medical imaging, so it can monitor enzymatic reactions and ligand binding, because on ligand binding and in the free ligand, the absorbance is going to be different, right? Because the structure is going to be different. Now, medical imaging, in vivo imaging of medical diagnostics and research, environmental monitoring, detecting pollutants and monitoring environmental conditions, etc. Cell biology, visualizing cellular components and processing with processes using fluorescent labels. So there are different fluorescent stains that are useful in visualizing your materials that are present inside the nucleus, and then the proteins that are present in the cytoplasm. You can tag these components with different dyes, like these fluorescent labels, and then you can visualize them under the microscope. All right, last but not the least is quantum yield. So quantum yield is the ratio of the number of photons emitted by the number of photons absorbed. This tells you about the efficiency of a fluorophore. So quantum yield 1 means all the photon that is absorbed is emitted, that is 100% efficiency, and quantum yield 0 indicates no fluorescence. Alright, so we will start with the questions. So the first question says, to record the fluorescent emission of lysozyme protein having phenylalanine, tryptophan and tyrosine residues, one should select the excitation wavelength for which of the following. Alright, so tryptophan residue. Since tyrosine and phenylalanine are non-fluorescent in lysozyme protein, all of them are fluorescent because all of them are having aromatic side chain. Okay, so this is definitely not correct, right? So this is not correct. We look at the next one, tyrosine. Since tryptophan and phenylalanine is not non-fluorescent, no, this is wrong. Then tryptophan residue, since tyrosine and phenylalanine have much lower quantum yield as compared to tryptophan. Either tryptophan or tyrosine, since phenylalanine is non-fluorescent. So I told you that none of them are non-fluorescent. So then we can consider this third option to be correct. And again, let us look at the option. Yes, so the third option is definitely correct. So that means tryptophan is having much higher quantum yield, which means that it can absorb quite a lot of light and then it can emit very high amount of light. So very less light is lost in the process, all right, compared to tyrosine and phenylalanine. So then third is the right option. Now we move on to another question. So questions on magnetic radiation. So type of radiation that often triggers molecular vibration is or are. First is X-ray, then there is microwave radiation, UV radiation and the infrared radiation. Which one do you think would be the answer? If you look at the EM spectra, so whenever these type of questions come, always look at the EM spectra. So this is the range of visible light. Here is your UV. Here is UV. So UV is having higher wavelength, and this is your X-ray. Okay. Here is infrared radiation. This is having very high frequency. And then there is microwave radiation. So there is microwaves and then there is radio waves. So that is the EM spectra, right? So then this is visible light. Visible light does not trigger molecular vibration. Now I told you few slides back that molecular vibration is basically induced by infrared radiation, because infrared radiation causes heating effect, and more molecular vibration means when a molecule is heated up, definitely it is going to vibrate more. So that is how you can remember this. So in whichever option there is 4, it can be the correct option. So this is either correct or this is correct. Now see 1, 2 and 4 they are saying are correct. Now X-ray cannot do that because X-ray is lying in this range, and these are all non ionizing radiations, and these are these are all ionizing radiations, and therefore the right option would be your infrared radiation and definitely microwaves. So then let us look at the answer. Yes, so 1 and 4, sorry, 2 and 4 are the right option. So microwave radiation and 4 is infrared radiation. So yes, they have given the entire spectra, and from the spectra you can find out that these are the ionizing and non-ionizing radiations, and therefore they are going to cause. So microwave includes molecular rotation and infrared causes molecular vibration, right? So molecular vibration is triggered by mostly infrared and also microwaves, right? So the next question, this is a very simple question. They have asked you, if an electron is transitioning from a non-bonding orbital to a pi orbital, ठीक है? So non-bonding is represented by N, and pi orbital is, you know, it is represented by the symbol pi. And then they have mentioned bonding and anti-bonding as well. So which one of these do you think would be the right representation? So always remember, when there is anti-bonding, that means this star would be there, okay? And non-bonding means there should be an N. So N to sigma star, that is not correct because it is a pi orbital, it is not a sigma, right? So this is the, now this is an anti-bonding orbital, sigma is anti-bonding, so N to pi star, this is your pi orbital anti-bonding. So that means the correct representation is this one, and that is the right answer. So in the next question, they are asking you about absorbance and concentration, right? So UV absorbance at 280 nanometer is primarily caused by the tryptophan residues present in the protein. The absorbance of X molar protein in the concentration in the experiment at 0.35 is 0.35 at 280 nanometer, which is measured using a cell of 1 millimeter path length. Okay, so the protein content in the cuvette is approximately what? So now they have given this epsilon, which is the lambda, which is the coefficient of extinction coefficient. So we know that absorbance is equal to C into L into epsilon. Okay, so epsilon of the protein, this is already given, so this value you put here, all right? And then they have asked, they have already given this value, which is the absorbance, so this value you put here, and then they are asking this concentration is unknown, and this also they have given, which is 1 millimeter. Okay, so they have solved it. See, so usually this is usually given in 1 centimeter usually, right? So this is always given in 1 centimeter usually. So if this value is not mentioned in a question, you assume it to be 1 centimeter. Now they have given 1 millimeter. So 1 millimeter is 10 to the power minus 1 centimeter or 0.1 centimeter. So this value 1 millimeter, this you put here as 0.1 centimeter, right? So that is 0.1 centimeter. Then what do we get? We get the value of concentration, right? And the concentration, the value is coming as 0.35 millimolar. Okay, so now this is a very funny question. Let's see what they have asked. So a student is going to measure the concentration of RNase A protein in distilled water. So there is a tube in which you are having the protein, this is the protein, and then it is filled with distilled water. All right, now what type of solutions would he use to conduct the experiments in the cuvette A and B? So there is a cuvette which is A, and there is another cuvette which is B. So for measurement of absorbance, first thing that you have to do is you mimic the conditions in which the protein is present. So that means this distilled water has to be added into 1 cuvette, and the protein, this has to be added into another cuvette. So again, distilled water in 1 cuvette and protein solution in 1 cuvette. Now let us look at the answers. So A is RNase A and B is distilled water. And then C1 equals to C2 equals to RNase A. I don't know from where C is coming. So A is equal to distilled water and B is equal to RNase A. So see, this one and this one is just opposite to one another, right? So now the interesting part is that they have not told you which should be reference cuvette and which should be the cuvette for sample. Therefore, the answer, if you look at this question, see, cuvette for reference and sample are not specified. So if you look at this diagram, this is the light source, this is the chopper, that means it is chopping the beam into two parts, right? So this is flame or furnace, this is containing the sample cell, and this is the reference cell, and then it is going and entering the monochromator. So that means what is happening, there should be one here containing RNase A and there should be one here containing your distilled water, but then they have not specified which one, and so therefore the answer should be not enough information. All right, then now this is actually a double beam splitter spectroscopy, spectrophotometer. Okay, this is the instrument used to measure your absorbance. Now look at this. So double beam spectrophotometer differs from a single beam spectrophotometer, since in the case of the former means the single beam, the former is the double beam spectrophotometer. So both sample and reference cuvette cannot be measured simultaneously. Reference cell lamp has a different wavelength from the single sample cell lamp. This cannot be true. The chopper splits the light into two parts which passes through the reference and the sample cuvette. Reference absorption is first recorded followed by the sample absorption. Okay, now this is the case in case of the single beam cuvette, and so therefore this cannot be the answer, right? Because they have asked you about the property of the double beam, and this is a property of the single beam cuvette. So when we are having only one cuvette, first you add this reference and then you add the protein. You remove the reference and then you add the sample. So this cannot be it, right? So both sample and reference cannot be measured simultaneously. That is also not true, because both can be measured simultaneously. This is definitely wrong because there is a single lamp, and so we are left with the third one, which says that the chopper splits this into two parts, which is very true. Look at this. So this is a schematic diagram of a double beam spectrophotometer. So the chopper actually splits it into two parts, and there is a single lamp. This is going the reference beam and the sample cell. Both of them can be measured simultaneously. All right. So this is actually the diagram of a single beam splitter, where you see there is only one single cuvette, and first you add the reference, then you throw the reference, and then you add the the sample. All right. This is how it is done. Okay. So this is a diagram to help you to understand these spectrophotometers better. So spectrophotometer is an analytical instrument used to quantify the analytes in a given sample using a beam light. Therefore, this technique measures the absorption of light by the sample. So here, see, in a single spectrophotometer, there is a single beam of light, there is no beam splitting, but in a double beam splitter, a double beam spectrophotometer, there is a beam splitting, and it goes to the reference and the sample. Okay, so the next question is a question on UV visible spectroscopy, and they are asking you which of the following statements is true in UV visible spectroscopy. Okay, so an absorption band at 190 nanometer is due to disulfide bridges between the two cysteine residues. The cuvettes are made up of quartz with two sides frost and two other sides transparent in UV visible. Okay, so the peptide bonds and chromophores with strong absorption bands. Okay, yeah, so peptide bonds are chromophores with strong absorption bands at 280 nanometer. This is not true, because 280 nanometer is given by tryptophan, which is having the aromatic side chain, right? So this is definitely not true. And then The weak absorption band for the peptide bonds come around 190 nanometer. So then I told you about the quartz prism, and when you the quartz cuvette, and when you look at the cuvette, two sides of it are made of quartz and two other sides are actually transparent. So yes, this is the right answer. All right. So next we go to another question. You can tell me if you want me to slow down, but I just want to complete with the questions so that we can end the class quickly. We still have quite a lot of questions left, so we should not be missing out on the questions because that is more important, right? So we will have a look at this. So which of the following statements is or are true? So monochromators are used to disperse white light into various wavelengths. That is definitely true. Okay, so this is true. One is true. This is definitely true. At low concentration, the light emitted from all parts of a fluorescence quartz cuvette can be considered to be almost uniform. Fluorophores and chromophores are the same thing. This is not. You will very soon learn why. The maximum excitation of the wavelength for tryptophan, tyrosine and phenylalanine are 258. Okay, so tryptophan 258 they are saying. And tyrosine is 275 and phenylalanine they are saying is 280. I am sure you know that for tryptophan, very soon we studied in the previous questions that for tryptophan it is 280. Okay, for tyrosine it is 275 and it is around 260 or 265 for phenylalanine. So this order is not correct. So that means this is also not correct, right? So your 3 and 4 are not correct. So any question that has 3 and 4, this is not correct and this is also not correct. So we are left with 1 and 2. Let's see what is the answer. So maximum excitation wavelength for tryptophan, tyrosine and phenylalanine they have given is these respectively, right? So just the order is changed. Okay, so fluorophores are fluorescent chemical compounds that can re-emit light upon excitation. We learnt about fluorophores just a few slides back. And chromophores are an atom or group whose presence is responsible for the color of a compound. So chromophore actually absorbs light and then it gives out light of a different color. Okay, so now definitely option number A is correct, and this table is going to tell you more about fluorophores and chromophores. Okay, so see, fluorophores, green fluorescent protein, this is a fluorophore. Okay, and all of these, everything is given here, so you can go through this. Since we are running short of time, I will not go through this in details. And heme group are blood. It is made up of hemoglobin and therefore it is red in color. So it is giving this red color and it is heme group that is giving red color. Chlorophyll plants are green in color because of chlorophyll and therefore this is a chromophore. Alright, this is what you need to remember. Chromophore is therefore different from fluorophore. And then questions on the, you go through this better. Okay, whenever you can get time, go through this in details. Now questions on UV visible spectroscopy. The amino acids absorb in the UV region, lambda max is 280. So this is the structure of tyrosine amino acid, if you remember from our previous class, that is week 2 class. So this is tyrosine, and which region of tyrosine do you think is responsible for this absorption at 280 nanometers? So it is this aromatic side chain, right? This aromatic side chain is nothing but the phenolic group. Okay, because COOH group is this one. This is not going to do that. NH2 group, no. OH group, no. At 280 nanometer, phenolic group or this conjugate double bond, they are involved in absorption, and therefore this is the right answer would be D. All right. Okay. So question on the UV visible spectroscopy. Which of the following statements is or are true? So in fluorimetry, photovoltaic cell and PMT, that is photomultiplier tubes, are used as detectors. So I think we saw in one of the diagrams that this photomultiplier tube, it was written there, that is used as detector. Okay. So when molecules are excited in the visible region, hydrogen deuterium lamp is used. Compounds having aliphatic carbonyl structure. Aliphatic is just not involving any C double bond O or ring structures. Okay, these are non-ring structures. So they are showing more intense fluorescence than the compounds having aromatic functional groups. So quantum yield quantifies the efficiency of luminescence. Okay, so if you remember from the previous classes, detectors definitely they use photomultiplier tubes. Okay, but then for visible region we were not using hydrogen deuterium lamp. For visible region rather we were using the tungsten lamp, and this hydrogen deuterium lamp, this we were using to generate ultraviolet light in UV visible spectroscopy. Okay, this is definitely wrong because we noticed just now here that this aromatic ring was giving more absorbance at 280 nanometer than the carbonyl aliphatic carbonyl structures, right? So this is wrong, and then that means 2 and 3 are wrong. Okay, so let us see 1 and 4 are correct, so maybe this is going to be correct. Let us have a look. When molecules are excited in the visible region, tungsten lamp is used, and compounds having aromatic functional group show more intense fluorescence than the compounds having aliphatic carbonyl structure. Okay, for fluorescence microscopy, xenon lamp is used, but for fluorescence spectroscopy, xenon lamp is used, but for absorbance spectroscopy, we use this tungsten lamp, right? So, if xenon lamp was written here, that would also be correct. Okay, so now this one, compounds with aromatic functional group show more intense fluorescence, right? So definitely 1 and 4 are correct and 2 and 3 are wrong. All right. So now comes another question. So a researcher has prepared a new drug molecule to study its interaction with the protein. The lambda max of the drug molecule is at 260 nanometer. The desired emission should start from. So this is the absorption spectra. Here is the emission spectra. I just told you about Stokes shift. So this is the graph. This they have said is 260, right? So they are asking you what should this be, and this is your absorbance or A, and this is your lambda, right, in nanometers. So this is the wavelength that is needed, that it absorbs, and this is the wavelength that it emits. So always remember this distance, it should be more than equal to 10 nanometer. So 260 plus 10, what should it be? It should be anywhere around here, right? It should start from more than 10. So that is 275. See here they have explained everything. The emission should start at least 10 to 15 nanometer ahead of the excitation wavelength. See, since in Jablonski diagram, the molecule once excited to S2 from S0, it comes down to the lowest vibrational level. So I told you this happens, but why exactly it happens, they have explained here. So it comes down to the lowest vibrational level of S1. The energy gap from S1 to S0 is lower than that of S2 to S0 to S2. Since hence the fluorescence wavelength is in the higher range than the excitation wavelength. They have given the formula, and therefore the higher wavelength should be avoided since one may miss the emission wavelength, right? So let's go back to this Jablonski diagram, right? So they are telling you that the energy gap from S1 to S0 is lower than that of S0 to S2. So this is S1 and S0, and this is S0 to S2. So it is undergoing this internal conversion and all, right? And so because of that, we might miss the emission wavelength if the two wavelengths are very, very close by. Okay. So that was the last question for today. If you have any other questions or any other suggestions, please let me know. From the next class onwards, I will try to keep the theory shorter so that we can spend more time on the questions. And thank you so much for being there in the class and for listening to me. You can ask me if you have any questions. So you can access the recordings from the YouTube channel into my bioverse. You can just type my name, Beas Mukherjee, experimental biochemistry. All that links will be provided to you by NPTEL team, and there you can access the PDF, you can access the recording sessions. All right. Thank you so much. If you have nothing to say, I will be ending the meeting.
Okay, thank you.
Thank you. Okay.
Okay, thank you.